Okay, so the ceramic crystal structures can be quite varied. We're going to study just a few of the variations, and we'll start with the AX-type crystal structure. The AX-type crystal structure really means that we have an equal number of cations and anions. The A denotes the cation, the X denotes the anion numbers, of course. For example, if we look at the sodium chloride structure, we have a sodium cation and a chlorine anion. Let's investigate the actual geometry of the structure down here. And the rock salt or sodium chloride structure is comprised of two interpenetrating FCC lattices. One lattice is composed of cations and the other is comprised of anions. Let's check out what that means. If we look at all these blue spheres here, these blue spheres seem to be components of a face-centered cube, do they not? We have blue spheres on the faces and at the corners. Now let's stick the cations, the smaller cations, the sodium cations, at the junctures that are in between the blue spheres. So the blue spheres represent the anions, and we're going to stick the little black ones in between, which represent the cations, and we're going to put them in all the junctures between where you have blue spheres forming sort of aligned with each other. Okay. Now, this itself doesn't look like a face-centered cube for the sodium, but if we were to flip things around, so we put the black where the blue is and the blue where the black is, and then we add them together, you're going to have the same sort of crystal structure. So you can think of it as either the blue spheres in a face-centered cube with the black in between, or vice versa, the black on a face-centered cube with the blue in between. And the coordination number for this type of structure will be 6, and the best way to see that is if you look at the central black sphere here, which is the sodium cation, then what are the number of nearest neighbor anions? Well, they're all the face-centered ones. Alright, so I can have this one at top, this one at the bottom, that's 2, this one at the front, this one at the back, that's 4, this one to the left here, this one to the right, that's 6. That gives me a coordination number of 6. And based on the table that we talked about earlier, the ratio of the cation radius to the anion radius falls between 0.414 and 0.732 based on the coordination number. The common ceramic materials with this type of structure would be sodium chloride, of course, magnesium oxide, these others. Iron oxide is particularly useful, or often it is a byproduct in industry, or actually used to manufacture various materials. Okay, the next one we have is the cesium chloride structure. It looks very much like a BCC crystal structure, but the ion in the center is not the same as the ions at the corner positions. So notice I have anions, chlorine anions at the corner positions, and the ion in the center is a cation, it's a cesium cation. So obviously the coordination number is 8 here, right? Because we have 8 blue that would be contacting the 1 cesium. And of course, this is the basic unit cell. So if you were to add these all together, you're still going to have a 1-to-1 ratio of cesium chloride, of cesium to chlorine. And you can kind of see it here too, because there's only 1/8 of each chlorine anion that is inside of this unit cell. And then we have 8 corners, that makes 1, and then we have 1 cesium, so that's 1 there. So that's still a 1-to-1, so it's still an AX structure, even though it looks like this. Okay, the zinc blend structure, the coordination number is 4, and the unit cell looks something like this, where we have tetrahedral bonds being formed between the cation and 4 anions. So if you look, let's say down here, let's check this little zinc cation out for a second. If we look at the corner, it bonds with this one, then it's gonna be contacting the nearest neighbors, which are the face-centered anions closest to it, and those would be this face-centered one here, which is on the same face, the left face here as this one, and this face-centered on the back face, and this face-centered on the bottom. Okay, and then it's sort of symmetrical if you are on this side. Then if you take a diagonal coming from this anion and you go all the way across, you have the same pattern. That's what I'm saying. You have the same pattern. Same thing if you go over here, you take a diagonal from this one and you go all the way across to this one, you have the same tetragonal pattern. Okay. Alright, now the AMXP type crystal structures. In these structures you don't have the 1-to-1 ratio anymore. So for example, you may have an AX2, such as calcium fluoride. We can look in our table that we discussed earlier, and we see that the coordination number is 8. And the structure for the calcium fluoride is similar to the cesium chloride, except that we have half as many calcium ions as there are fluorine ions. Why? Well, because it's a 1-to-2 ratio, 1 to 2. Right? So half as many calcium as we have fluorine. This is what the structure looks like. Very similar to the cesium chloride, but we're going to take a single unit cell and put it together with itself 8 times. So we have 8 of those cubic cells, and that really makes 1 unit cell for the calcium fluoride. And if you look, you'll see this is the only way we can balance it, so that we have a 1-to-2 ratio, where we're going to have cesium, not cesium, we're going to have calcium cations in only, as being the body-centered entity, in only 4 of the cubic cells. Remember, we have 8 cubic cells, but we want cesium cations as being the body-centered entities in 4, so that gives us our 1-to-2 ratio. And this table 12.4 sort of summarizes what we just discussed. Notice that the coordination numbers are different here for the fluoride, which is an AX2 type structure. So we see the coordination number for the cation is 8, while the coordination number for the anion is 4. And why is that? Again, we go back to that 1-to-2 relationship. Let's go back here. We said here at the bottom there are half as many cations as there are fluorine anions. Okay. So that means if we have half as many cations, then they'll be touching twice as many anions. So their coordination number will be 2 times the coordination number of the anions. So it'll be, their coordination number will be 8 versus the anions. Sorry, I said there'll be 8 versus the anions, of course, whose coordination number is 4. Alright, so quick example on the basis of ionic radii. What crystal structure would you predict for iron oxide? Well, we can, we have the radii here. So iron oxide uses this isotope of iron, Fe2 plus and oxygen 2 minus, and we see that the radii ratio of cation to anions gives us 0.55. We can go to our table and see where the 0.55 ratio falls. And from the table, it falls between 0.414 and 0.732, which gives us a coordination number of 6. How about calcium fluoride? What crystal structure would you predict for calcium fluoride? Let's say you did not know. We just looked at it, so we know what crystal structure it is, but if we didn't know, what would we do? Well, again, we look at the ratio. We look at the ratio of cations to anions, and we get 0.752, and we can go to the table again, and we see that the coordination number for the cations is 8. So remember, we sort of mentioned this before. If the coordination number for the cations is 8, but you have a half as many cations as you have anions, then the coordination number for the cations must be twice that of the anions. So we should have 4 anions. Alright, so let's talk about density. The density computation for a ceramic is very similar to what we did with a metal. The only difference is that we have 2 different entities, the atomic weights of different entities that we have to consider. Of 2 different entities, we have to consider the atomic weights of the cations and the atomic weights of the anions. And the formula is pretty much the same, because we're looking at what? The mass over the volume. What's the mass? The mass is going to be, of course, the atomic weight divided by the amount of cations or anions that are in the atomic, that would weigh that amount. So clearly, that would give us our mass of a single cation or a single anion. Okay, and then we'll multiply that by sort of the number of cations and anions that are present, that n prime. So let's look at a quick example. Here's our example. Alright, so let's say that rock salt structure, what is the number of number of atoms, number of ions in this unit cell for let's say for the cations. The cations are little black ones, right? If you see the black ones here at this juncture, what portion of it is actually inside the cell? Well, you have 2 planes perpendicular to each other cutting into that sphere at the center. So you're really just going to have a quarter of this sphere inside of the unit cell. And then we have 12 of these. There are 12 of these in the same, very similar position, or same, where only a quarter of them are actually inside the cell. So for the cations, we have 12 times a quarter plus that central cation, 1 times 1. Okay, so I get my number of formula units to be 4. Okay, and it's a 1-to-1 ratio, so clearly the number of chlorine anions is also 4. Right, and you can see chlorine is easy as well, or it's easier because it's 1/8 at the ends that are inside, and then in the face-centered, a half of them are inside, and there's 6 face-centered spheres. Okay, so we get 6 times a half plus 8 times 1/8, which gives us back 4. Okay, we know the atomic weights of the cation, which is the sodium. We can look that up. The atomic weight of the anion, which is the chlorine. We can look that up. Okay, and then remember, what do we want? Density. Well, we know that the volume, we're talking about a cubic cell again, so the volume would be A cubed, where A is the characteristic length of the cube. I can see here that A is going to be the sum of the radii, or the diameter here, plus the 2 radii, so really the sum of the diameters. From the table, we can look up the diameters, and then we can plug in to get our theoretical density. We can plug in our R's to get our volume, and then we know the atomic weight. We know Avogadro's number, 6.02, and our n prime is 4.